Okay, we're going to continue on here, chapter 11. And last time we talked about, we started talking about modern atomic theory, and we talked about sort of the idea of as electrons, for example, sort of transition from, say, a lower energy level to a higher energy level, or as they transmit back down to a lower energy level if they happen to be in a higher energy level. Uh, the requirement here is that when an electron is in a higher energy level and it drops down to a lower energy level, the atom will emit. So it's an emission of energy in the form of a photon of light, which is a wave that will come off. Obviously, as the electron goes from a lower energy level to a higher energy level, that's what's known as an absorption. Has to basically absorb energy. But as it drops back down to a lower energy level, that is an emission sort of spectrum. Now, we talked about the idea that electrons in elements sort of gain energy in the form of what is referred to sometimes as a quantum of energy or a quanta of energy. And the idea of this, as we talked about, is again sort of like that staircase sort of description. Again, electrons will pretty much gain or lose energy, and they'll gain or lose enough energy to fully transition from one energy level to the next. Again, like walking stairs, you have enough energy really to go from step to step. You don't, again, sort of find yourself between steps or anything like that. And that's how electrons will sort of transition. They will go for example, this energy level here all the way down to that energy level. They will not like stop halfway between or anything like that. So they're going to either sort of fully transition upwards in energy or downwards in energy in terms of energy levels. We can look at the wave here, and the wave does have some properties that are important that we talked about. First off, there is the wavelength, which is lambda, and that is the distance between two peaks or two troughs, if you will, coming in this direction. Thank you. We also have the amplitude of a wave, which is basically from the midline to the peak of it. There's also the frequency of a wave, which is new. Typical units of wavelength a lot of times are meters. Also, nanometers are very common. Frequency typical units are reciprocal seconds or a hertz. And one reciprocal second is the same as 1 hertz. So it's a one-to-one relationship between those. There's a relationship between the wavelength and the frequency, and that is equal to the speed of light. So C is equal to the wavelength times the frequency. And the speed of light is a constant value, 2.99. I forget what number they use. 79, I want to say they use, I think, right? Is it 79, isn't it? Yeah, I think so. Yeah, actually. Sorry, I usually use the rounded three myself, but I believe that is the number they want you to use here. Meters per second. And so that's the value that you always have. Again, they typically will not give you that value in the problem. They typically won't even mention really the speed of light in the problem. They just assume that you kind of know that, and they do want you to know that, by the way. Here. And that allows us to, if we know the frequency, we could solve for the wavelength, which would be C divided by the frequency. And if we know the wavelength, we can solve for the frequency, which is C divided by the wavelength. Remember that when we are using the speed of light, because the units are meters, the wavelength has to be in meters. So again, common units of wavelengths are meters, but they can be centimeters. They can also be nanometers, and these are common units of wavelength. So if you have it in some other unit other than meters, you do need to do that conversion. Otherwise, it will not cancel out correctly with our speed of light. Now, we can also calculate the energy associated with these waves that are coming off, and the energy is equal to E times H energy is equal to h times the frequency. H is also another constant. This is Planck's constant, and also a number they expect you to know, which is 6.63 times 10 to the minus 34 joules times seconds. And that means if you do know the frequency of the wave, you can figure out the energy associated with that photon of light coming off. Using the equation above and this equation, so if we take where we solve for frequency, we could actually substitute that into here. And you could also see this equation hc divided by the wavelength. And what that allows you to do is, because h and c are both constants, if you know the wavelength, you could also calculate the energy associated with it as well, as the top ones there are both, again, constants. The energy will end up in terms of units if you just do either one. So that's joules times seconds. Our C is meters per second. And again, here our wavelength would has to be in meters. The seconds will cancel, the meters will cancel, and you'll be left with joules, which are the units of energy coming off here. Now, the relationship between sort of wavelength, energy, and so forth is, if you have something with a sort of longer wavelength, you also have usually a lower frequency, and that usually results in lower energy, as opposed to something with a much shorter sort of wavelength. So if you got something with kind of a short wavelength, that usually has a higher frequency, and that usually results in higher energy. So we also talked about the idea that as these electrons, for example, are transitioning and giving off this energy in the form of a light, we do see it can fall anywhere on the electromagnetic spectrum. And the electromagnetic spectrum is basically different parts of sort of radiation that comes off. And it goes from, for example, radio waves on sort of the longer wavelength end of it, all the way down to gamma rays on the very short end, including the part of the electromagnetic spectrum where we see color, which is the visible part of the spectrum. And in the visible part of the spectrum, that's where we see like our Roy G. Biv, right? And again, if this is, say, the longer wavelength side, and this is the shorter wavelength side, this is something like 700 nanometers to about 400 nanometers on this end. And again, usually the visible part of the spectrum is given in nanometers. So a reminder that nano is 10 to the minus 9, that conversion. And that's usually what visible part of the spectrum is. So if that energy coming off in the form of a photon of light has a wavelength that falls somewhere in this visible part of the spectrum, again, you will see that color obviously come out. Now, even colors here do have sort of differences in terms of energy. So red being at a higher wavelength or longer wavelength would be lower in energy than, say, violet, which is a shorter wavelength and would be higher in energy. And that can directly sort of help you understand maybe some of the colors that you might see in some spectrums. As we might have talked about, you know, if we had an electron that was way up here in this energy level and dropped all the way down to, say, that energy level, that's a lot of energy levels that basically it had to go through. And that's going to be a lot of energy that's going to have to be given off by the atom. And that would probably result in some type of color closer to the shorter wavelength, higher in energy, as opposed to if we saw an electron only, say, transition one energy level, that's not as much energy as the other guy. And it's not going to give off as much energy, and that might be more towards this side of the visible part of the spectrum in terms of the color that you may see, as it will have a longer wavelength and lower energy. Speaking of sort of spectrums, when we do excite something like, for example, an element and the atom of those elements, the electrons do sort of transition from higher energy levels back down to lower energy levels after they're excited, because everything wants to be in the lowest state of energy possible. So even though you kind of do something to it, like add energy to it, like in the flame test, when you put it in the flame, you added a lot of energy, obviously. those electrons will get excited to higher energy levels, but eventually will drop back down to lower energy levels because that's essentially where they want to be. So when we have those things, elements, for example, give off a spectrum which is known as a line spectrum, as we were talking about there towards the end. And because these elements have quantized energy, those electrons will again fully transition, from one energy level to the next. And the result of that is you get a very sort of clean sort of spectrum, if you will, of specific lines coming off at specific wavelengths and will have specific colors. Again, if you look at it, say, through a prism like that, and it kind of spreads out the light. And that's different than a continuous spectrum. And in a continuous spectrum, kind of like things like the sun, for example, uh, pretty much you have all sort of wavelengths coming off. And I think I use the sort of ramp analogy rather than a staircase in this type of situation. Again, on a ramp, you pretty much can stop anywhere along the way, as opposed to fully having to transfer, say, from one whole energy level to the next. So that's sort of the difference between it. And line spectrums for elements are so specific that each element has its own unique line spectrum. So depending on the colors of the lines that you see, what wavelengths they sort of come off at, you could actually identify what element you're dealing with, because everybody will have a different sort of line spectrum. Any questions on any of that stuff we talked about last time there? Okay. So speaking of that, that's the idea here of if we take like an electrical discharge tube, and here, like white light, like the sun, we get like all the colors sort of coming off like a rainbow, if you will. Here, if we take an element like hydrogen that's in this tube and we run an electrical current through it, that's going to excite the electrons. You can look at it through a prism, and what you'll see here again is you'll get these unique sort of lines coming off in the visible part of the spectrum at specific wavelengths. And each of these lines, these are the 4 lines there in hydrogen, for example, correspond to electrons transitioning from different energy levels. So the purple line, again, is probably a transition where it's going from a good number of energy levels, while the kind of orangey line there on the right is closer to the red part of the visible part of the spectrum. So that's an electron dropping probably not too many energy levels and giving off more of that orange color. Here, maybe 3rd time's charm.
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
So that again is your 4 distinct lines that we see in the hydrogen. And this idea of why we see these lines was sort of thought up by Bohr and sort of his theory of the hydrogen atom. And again, each of these lines do represent basically electrons transitioning from different elements. And Bohr's idea of the sort of hydrogen atom is really complicated, so we're not going to go into super detailed about it. And one of the things about Bohr's model is it is not so correct in all aspects. The main aspect is it doesn't really hold up very well once you move past any element that has kind of more than one electron, like hydrogen. So it works really well to sort of explain what we see in sort of hydrogen's line spectrum, but it doesn't really hold up as you move apart it. So his idea of sort of the hydrogen atom is what is sometimes referred to as a planetary model of it. His idea was that we had our nucleus here, which had our positive charge, and we had these different orbits around the nucleus. And we had electrons basically, obviously, orbiting around in these orbits and basically moving in a nice sort of circular pattern around it. He had different energy levels. N equals 1, for example, is the ground state, and it is the closest to the nucleus. And then there's n equals 2, 3, 4, 5, 6, and 7. These are what are referred to as excited states, which are higher in energy. So for example, we have like n equals 1, n equals 2, n equals 3. So his idea of sort of how electrons are moving around the atom is in these orbits, and they're either sort of fixed in one sort of energy level or the next. So, for example, if you had an electron over here, it would be transferring, again, losing enough energy, for example, to get all the way down, for example, to the first energy level. That loss of energy that's coming off would account again for sort of one of those lines that we see in the hydrogen spectrum that we just looked at as a result of the photon of light that's going to come off. So the idea here is with Bohr's model that, you could almost like put your finger on the orbit and it'll eventually come back around, right? So this idea that we kind of know exactly how the electron is moving around in the atom and in these orbits. And again, we might have an electron here, and the idea it drops down, or maybe an electron over here, a little bit more energy levels dropping down. But an electron would be found, according to Bohr, either in this orbit, or this orbit, again, orbiting around. Once again, they would not be sort of in the middle of any orbits or anything like that. And in the energy difference, as they kind of go from one energy level to the next, is equal to that sort of equation that we talked about earlier. You could calculate that. That's sort of what is known as sort of a packet of energy or quanta of energy. Again, they're going to gain or lose energy in that fashion. By the way, if they were going in the opposite direction, they would be going obviously upwards in terms of energy as well. So the emission of radiation in a hydrogen atom, again, is a result of those electrons being dropped from a higher energy level to a lower. Here, we're maybe only going one energy level. So maybe we see a red photon of light coming off, as that's not a big energy transfer. It would give off probably a wave with a longer wavelength, maybe closer to that red toward part of the spectrum. Now, as I mentioned before, that n value is the energy level, and n is really what is referred to as the principal quantum number. There's actually 4 quantum numbers, which we won't really get too much into, and n is the principal quantum number. It is a fancy word really for the energy levels. So these are the different energy levels at which electrons can be found within the atom. Once again, n equals 1 is the ground state. That is really the one that is closest to the nucleus. And anything sort of above that is referred to, as I mentioned before, as an excited state or an excited level. And that's higher in energy and further away from the nucleus. Essentially, n can have values of 1 through 7, basically. And if you're on, say, n equals 7, you are much farther away from the nucleus than if you obviously are like n equals 2, you're much closer to the nucleus. And here again, we can see, as we were talking about, this guy is transitioning a lot further down. And again, that's going to give off a wave with a lot more energy and a shorter wavelength. So again, if it falls in that visible part of the spectrum, maybe here, as you can see there, we see more of a blue color of light coming off, rather than, again, this kind of shorter transition of energy, which would correspond to a longer wavelength and red. Now, not all electrons, as they transition down, for example, from different energy levels, will always give off energy in the form of visible light. So they could actually give off waves that fall anywhere in the electromagnetic spectrum, like we saw earlier. They could give off energy in the infrared spectrum, where you would feel heat. They could give it off in the UV part of the spectrum. So only ones that obviously drop out into that visible part of the spectrum where the wavelength is, those are the ones that we would see color associated with. And here are the 4 excited states in hydrogen. And again, each of these transitions from these different energy levels, if that's n equals 1, n equals 2, n equals 3, n equals 4, each of these will result in those 4 line spectrums that we saw, those 4 different sort of lines that happen in hydrogen, and each of them are accounted for by these transitions here of these electrons. And again, here on the left is more of a continuous energy level and a more quantized energy. So again, elements do this quantized energy where they will drop from here to here or to here. Here, as you can see, pretty much you could stop anywhere along the way here in a continuous spectrum. And again, that's what sort of gives everything coming off at once, because you have basically all the waves coming off. Yeah. The quantum energy, the line spectrum is a result of the energy being quantized. Yeah. So, and that's why, again, we get these distinct, just individual lines coming off, because it corresponds to the full transition, basically, of that guy, say, going from there to there. And that results basically in one line that you see on that line spectrum, basically. Here, again, because, it could it's picking up energy all the way through, basically, and it can stop any way through here. We get more like the first part of that picture where you saw kind of the rainbow color coming out, or like everything coming out at once. And again, because there's no distinct sort of stopping point, if you will, right? It's just like in the stairs, you go from one stair to the next. That's like your stopping point. On a ramp, again, you could like walk and stop every 2 seconds, right? And there's no kind of distinct, definitely cut off of energy that's going to happen in that transition. Other questions? There's our ramp versus our stairs. So we're going to talk about the wave mechanical model and sort of the idea of Bohr. For example, as I mentioned, it works really well to describe those 4 lines that we do see in the hydrogen spectrum, but it does sort of fall apart as you move away from hydrogen and things that have more than one electron. So what people started to do was to sort of theorize and do experiments where they're trying to kind of move away from maybe Bohr's idea as it not being sort of correct in every sort of aspect. So one of the early sort of ideas of moving away from sort of Bohr's model of, I know for sure that the electrons, which are particles, are in these orbits and they're just going around in circles in each of these orbits, was done by de Broglie. And de Broglie basically had this idea that particles like electrons can have a kind of dual nature of wave-like functions. So there was a lot of work done by Einstein, de Broglie. He actually didn't do a lot of work. He actually just theorized it. Other people later on did the experiments. But the idea was this, that, the idea of particles can have both particle-like function and also wave-like characteristics. And waves could also be thought of as like a stream of particles. So this kind of dual nature of light, this kind of wave and particle nature of it. And what de Broglie said was that an electron, which is a particle, is bound to the nucleus like a standing wave. So what's a standing wave? Like on a guitar, right? You got a string, and if you pluck it, you got a wave that happens, right? But the wave goes nowhere, right? The string doesn't pop off and keep going or anything like that. So if you pluck a guitar string or something like that, you'll have a standing wave. And this standing wave will have points which are known as nodes. It has no amplitude. And so sort of this idea of, well, maybe these electrons are not moving around these pretty orbits, but they have more of a wave-like characteristic, really started with de Broglie. So if you think about it, again, there is the nucleus, and we have this electron, and it's sort of bound to the nucleus more in this wave-like characteristic as it's moving around. That's what keeps sort of the electron, for example, from just flying away, all of them, right? Is there's some type of attraction to the nucleus, and that's going to be a point of, like on the guitar, where your string is attached to the guitar so it doesn't go away. That's sort of how the electron is sort of related to the nucleus. Now, as I mentioned before, there are points along the way in this sort of standing wave model where there's no amplitude. And we sort of think of these sort of as we'll talk about, kind of places where, like the nucleus, for example, is. Now, de Broglie reasoned that basically waves can have behave like particles, and particles can exhibit wave type properties. And this was a really big sort of step forward from Bohr's idea that it's just a particle hanging out in an orbit, kind of going around in circles in these pretty orbits. The next sort of big idea that helped us sort of move away from Bohr's model of the atom was Heisenberg and the Heisenberg uncertainty principle. And basically, the Heisenberg uncertainty principle says that it's impossible to know exactly how a particle, like say an electron, is moving. So, and its particular location. So the more that you know about how a particle like an electron is moving around, the less you know about its actual location of where it's at, and actually vice versa. The more you know about sort of the location of where you think the particle like an electron is moving in the atom, the less you know about how it's actually moving and how it's sort of moving around in that particular space. So with the idea of de Broglie, where particles like electrons can have wave-like function, with the idea of Heisenberg and this uncertainty principle, we are more and more really moving away from Bohr's model of electrons in these orbits. So we're kind of moving away from his idea, as again it holds really good for hydrogen, but again sort of falls apart as you move away from it. The next really major step that moved us sort of completely away from Bohr's model of the atom was one that was done by Schrödinger. And Schrödinger had a bunch of equations, and these are wave-like functions. And if you ever take physical chemistry down the road, you'll learn all about these sort of calculus type of mathematical equations. But needless to say, the idea of his wave-like function is that, again, we're moving away from this idea of we know for sure electrons are in these orbits, and they're going around. We're moving away from this to this idea of what really Schrödinger's sort of idea is, that the best that we could do in terms of the electron and sort of its location and maybe where it's at is probability. Like there's either a really high probability that you could find an electron in a particular spot in the atom, or there's maybe a lower probability that you could find an electron in a particular part of the atom. So we know just by the idea of the nucleus is positively charged that there should be a pretty high probability of finding an electron somewhere near the nucleus, right? Because electrons are negatively charged, the nucleus are positively charged, so there's going to be an attraction between them. And as we fan out from the nucleus, which I can't really draw so well, but imagine it getting lighter as you kind of move away from the nucleus, the probability of finding an electron further away from the nucleus is a lot less than it is closer to the nucleus. Does that mean you can never find an electron far away from the nucleus? The answer is no, you can. It's just a lower probability than if you're near the nucleus. There's probably a greater chance you're going to come across an electron. Now, the major difference as we move to this quantum mechanical model from Bohr's idea of orbits and things going around pretty circles is this idea of Heisenberg's uncertainty principle, which is even though there is a very high probability of finding an electron near the nucleus, we still have really no idea where it's exactly at and how it's exactly moving. We just know that if we're in that area, at some point, there should be an electron that probably should pass us by at some point. And it is moving pretty randomly about the nucleus. And same idea as we kind of go further away from the nucleus, you know, there's probably a lesser chance we might have to wait longer for an electron to come by. But again, we don't really know exactly where it's going to come or how it's going to be or exactly its location. So with this sort of probability, we actually move away from the idea of electrons in these kind of known orbits traveling around like in Bohr's model in pretty circles to this idea of what are referred to as orbitals or atomic orbitals. And atomic orbitals are theoretical probability maps within the atom of where you would find electrons basically housed. So they're basically just like electron density maps. Like there's a pretty good probability of finding it there. Again, we still don't know how it got there. We still don't know how it's traveling. So again, we're moving away from this idea of they're moving these pretty circles to this idea that we have electrons, again, pretty randomly about moving around the nucleus, again, in sort of these atomic orbitals, sort of theoretical maps. Any questions on that there? And here's sort of an electron density map, and you can kind of see that, I think, on the screen. Obviously, the nucleus would be right around here in the middle. I guess red on red wasn't the best choice, but I guess you can see it. And as you can see, as you sort of fade out from the center, which would be kind of where the nucleus is, it gets lighter and lighter in terms of that. And the pink area there is the electron density. So the darker the area, the more higher probability of finding an electron. And as you can see, as you sort of fan out towards the edges and away from the nucleus, it gets lighter and lighter. And there's, again, a less of a probability of electrons being found in that particular location. So let's talk a little about these atomic orbitals and the different sort of places that we do find electrons. Now, the first type of orbital that we have, and by the way, when we talk about atomic orbitals, any individual atomic orbital can hold a maximum of 2 electrons. So any individual orbital that you have, no matter what energy level it is, no matter what type of orbital it is, the maximum of electrons that you can put in there is 2. So if you think about it, like if this represents an orbital, you basically can only put 2 electrons. If each arrow represents an electron, that is maxed out basically that particular atomic orbital. So the first type of orbitals that we have actually begin on the very first energy level. So n equals 1 is the lowest energy level. And this is where s orbitals begin. And an s orbital is merely a sphere. It's basically just a circle. And there is an s orbital on every energy level. So 1 through 7, you will find s orbitals present. They are just labeled differently. So on the first energy level, it's known as a 1s orbital. The 1 means it's on the first energy level. On the second energy level, it gets a little bigger, by the way, to accommodate all the electrons. It's known as a 2s orbital because it's on the second energy level. And then it just continues down 3s, 4s, 5s, and so forth. So on every individual energy level, you'll find different orbitals. Actually, on the first energy level, that is the only type of orbital that you find. There's just an s orbital. Now, in terms of s orbitals, there's only one type of s orbital, which means if I maxed out my s orbital on any energy level, my maximum number of electrons is going to be 2 that I could put in there. And on any energy level, you only find one s orbital, one individual s orbital. And that one individual s orbital can only hold 2 electrons. So that will fill it up on any energy level that you have. Here's what it looks like, as you can see there.
An s orbital has a spherical shape with the nucleus at the center.
And again, that's basically like a probability map of finding an electron. So it's based on like the Schrodinger type of equations. And again, you can kind of see the overlay of the probability map there on the left and kind of the spherical size there or shape of the s orbital. And as I showed you a second ago, they kind of increase in size. Again, as you go up different energy levels, there's a lot more electrons that have been put in there. So they got to kind of get bigger and bigger to accommodate all the electrons that are happening. But the shape is essentially the same shape. The next type of orbitals that there are p orbitals. And p orbitals start at the n equals 2 level. So that is the next energy level up, the second energy level. That is where you first start to see p orbitals. So on the first energy level, all we have is a 1s orbital, like we just talked about. On the second energy level, we still have an s orbital, but that is a 2s orbital. And what happens now on the second energy level, that is where we first start to see p orbitals appear. Now, p orbitals, as we'll see a picture, are kind of like figure eights, if you will. They kind of look like that. And you can kind of think of the nucleus as being kind of there. And the highest probability of electrons kind of like in that area near where the nucleus is. Now, p orbitals, unlike s orbitals, there's actually 3 different types of p orbitals. So when we get to the p orbital on the second energy level, there's actually 3 individual p orbitals. There's a px orbital, a py orbital, and a pz orbital. And each of these basically correspond to 3-dimensional space. Like in math, there's an x, y, and z axis. If you draw like a plane, a Cartesian plane. And each of these are in 3 different spots there in 3-dimensional space. Now, when we have orbitals where there are multiple orbitals, this is what is sometimes referred to as a subshell or sublevel, depending on your book. So this would be referred to, for example, right here, all 3 of those orbitals together would be referred to as the 2p subshell, for example. We do not use the word sort of subshell or sublevel for s because there's just one orbital, so it's just an individual orbital. But whenever you have a grouping of multiple orbitals on the same energy level that are the same type of orbital, they're referred to as a subshell or sublevel. Now, because of that, if I maxed out all of the orbitals in the 2p subshell, how many electrons would I be able to put in there? It would be 6. That is 1, 2, 3, 4, 5, and 6. I can max it out with 6 electrons if I filled basically the entire 2p subshell with it. Any questions on that there? And here's a few diagrams of what they look like there.
The 2px orbital is in the shape of a figure 8 along the x-axis.
Then obviously we have our 2py, same idea, just different orientation.
Is in the shape of a figure 8 along the y-axis.
And then obviously here we have our z. Again, same shape, just different.
The 2pz orbital is in the shape of a figure 8 along the z-axis.
And again, sort of those lobes, which are the circular parts of it, that is the area where we would expect to probability find an electron somewhere located. You can think of where the center is, sort of where the nucleus would be sort of housed, and again, the probability of finding those electrons. As you can see here, again, kind of like the nucleus here, higher probabilities near the nucleus. Again, still do not know in the quantum mechanical model how they're traveling, where they're located. But again, just the idea of probability of finding an electron in those areas. The next set of orbitals that appear happen on the 3rd energy level. So on the 3rd energy level, that is where we first start to see d orbitals. And on the 3rd energy level, we see these d orbitals. And if we kind of add to our little picture, on the 1st energy level, we have a 1s orbital. On the 2nd energy level, we have a 2s orbital in our 2p. Now on the 3rd energy level, we also still have a 3s orbital. We still have our 3p subshell. Again, the numbers has changed to 3 because we're on the third energy level. And this is where we first start to see 1, 2, 3, 4, 5. That's where we first start to see d orbitals first appear. There are 5 different d orbitals, as you can see down here. These are the 5 different d orbitals. And again here, because there are 5 different d orbitals, each could hold 2. That means if we max out electrons here for this d subshell, right, all those together would be, again, a subshell or sublevel. We maxed out how many electrons? If I maxed all that out, it would be 10, right? 1, 2, 3, 4, 5. Then they could have 2, so 6, 7, 8, 9, and 10, right? So we basically can, in each of those orbitals, stick 2 electrons in there, and that would max us out at 10 electrons here if we fill the entire 3D subshell. Obviously, in this case, energy is increasing as we go up, and we are also moving farther away from the nucleus as we kind of continue up the different energy levels. What do d orbitals look like? As you can see in the picture, they kind of look like 2 p orbitals stuck together, basically. So there's kind of like 2 p orbitals basically stuck together, as you can see here.
Y squared orbital has a cloverleaf shape that lies in the xy plane and is aligned along the x and y axes.
And
the 3D x squared minus y squared orbital has a cloverleaf shape that lies in the xy plane and is aligned along the x and y axes.
You can see they all kind of look very similar.
Is a cloverleaf shape that lies in the xy plane and bisects the x and y axes. The
3dxz orbital has a cloverleaf shape that lies in the xz plane and bisects the x and the z.
And then this is the only one that kind of looks different. Kind of looks like a donut there, as they describe it, with a p orbital in it.
Is shaped like a pz orbital with a donut of electron density around the center. It is aligned with the z-axis.
Now, lastly, the last set of orbitals that we usually deal with are f orbitals. And that does not occur until you get to the 4th energy level. So on the 4th energy level, that is where we start to see f orbitals appear. There are 7 degenerate orbitals, which means they're kind of on the same energy level, basically. And that means, again, if we sort of add to our picture, on the 1st energy level, we have the 1s orbital, 2nd, 2s, and r2p. On the n equals 3, r3s, 3p, 3d. And now on the 4th energy level, we still have a 4s, we still have a 4p, we still have a 4d, and I ran out of room, but right about here, we will have R4f, and there should be 7 little dashes going that way. And that's where we start to appear our 4f sort of orbitals. You go 4f, 5f, 6f, 7f. In most cases, you don't go past 5, but you can go that way. Now, this only got us to the 4th energy level. There's a 5th, 6th, 7th energy level. You'll never see it in any classes that you take, but there are orbitals that are in these different energy levels as you continue up. What essentially happens is you just go alphabetical after F, and those are the orbitals, but we never use them for really anything in terms of electron configuration or anything like that. You would be kind of off the periodic table in terms of elements and stuff like that. But they actually do continue on to, for example, G would be next and stuff like that on like the 5th energy level and so forth as you continue up. But we really do sort of max out here in terms of orbitals that were commonly used for electron configuration at F. Any questions on that? So as you can see here, and as we were sort of drawing as we went through it, we have our different energy level, our different orbitals that are present. And in the case of, say, the hydrogen atom, what we actually see when we look at these orbitals is all of the orbitals are basically equal in terms of energy. Everybody on the second energy level, all the orbitals are equal. Everybody on the third energy level, fourth energy level, they're all equal basically as you go across. Now, when we talk about a like energy level, that is what is sometimes referred to. So for example, if I want to know the maximum number of electrons on the n equals 2, sometimes referred to as a level, or some people call it a shell. How many electrons if I filled up all the orbitals on the n equals 2 level or shell? When we look at a level or shell, we're talking about an entire energy level, and we're talking about everybody that is on that energy level. So the answer would be how many electrons if I filled the entire level up? Each one could hold, if each of these lines represents an orbital, each one could hold 2 electrons, right? So we could go 2, 3, 4, 5, 6, 7, and 8 electrons. Yeah, so if we filled that entire thing up, 8 electrons. You could actually calculate it without drawing it, because sometimes you might not want to draw it. So if you have that type of question, if you want to know the maximum number of electrons on a level or shell, you could just basically go 2 times n squared. N is the principal quantum number, or the energy level. You square it, then times it by 2. For example, the one we just did, n is equal to 2. 2 squared is 4. 4 times 2 is 8. Yeah. So if I were doing the fourth energy level, right? 4 squared is 16. 16 times 2 is 32 electrons. Yeah. So we can max out 32 electrons. Now, if I want to know again how many electrons in the 3D subshell, and also how many electrons in a 4p orbital, take a moment and answer that, and also how many electrons in the n equals 3 level. So if I wanted to fill it up there, so 3D subshell, that is all these orbitals, right? And a D subshell holds 5. And that means if I can put 2 in each, that should be 10, right? Electrons basically we can put into there. How many electrons in the n equals 3 level? That is everybody on this level, basically, right? So again, we can kind of do the math part of it. 3 squared is 9. 9 times 2 is 18 electrons, right? If we filled everybody up, basically 2, 4, 6, 8, 10, 12, 14, 16, and 18. If we put 2 electrons into each of those guys, yeah. Any questions on that one there? How many electrons in a 4p orbital? What would the answer be? The answer would be orbital could only hold 2 electrons, yeah? And that's because we don't know if we're talking about that orbital, right? That orbital or that orbital, the px, py, or pz orbital. If I asked you how many electrons in the 4p subshell, how many would it be? 4p subshell would be all of them together, which would be 6, yeah? So remember, any individual orbital, no matter what the energy level is, could only hold 2 electrons. Again, the subshell is a grouping of all the orbitals together, and that in this case would be 6 if we were asked that question. Yeah. What's that? If you're just looking for a subshell, you could calculate very simply by knowing, like we talked about, that S has only 1 orbital, right? The P subshell has 3, the D has 5, and the F has 7, and each orbital could hold 2. So basically, just times it by 2. So for each like subshell, for example. So like any P subshell, the 3p subshell would be 3 times 2 is 6, right? The 5D subshell would be 5 times 2 is 10. So it doesn't matter what energy level it is. So for the subshell, if you max them out, you basically just got to take how many orbitals there are times 2, basically. Other questions? All right, so when we look at this here, before I started drawing all over it, I suppose, when we looked at it, as I was mentioning before, how electrons go into the atom is they go in from the lowest energy level first, and then once that's filled, they then go to the next lowest, and then they kind of keep proceeding on and adding electrons in. Now, you do not have to fill up any particular orbital completely. You do not have to fill up a subshell completely. You basically just kind of put your electrons in, lowest energy to highest, until you're out of electrons, essentially. Now, as I mentioned before, when you look at this here, you could see that the orbitals are all basically equal in energy. Everybody on the third, they're all perfectly equal in energy. But what happens when you have more than one hydrogen, like one more electron, or have more than one electron, like we see in hydrogen? What happens is when we get a lot of electrons there, we have a lot of negatively charged particles, which ultimately do not want to be near each other. So they're going to try to get away from each other. And what ends up happening is the orbitals themselves actually start moving in energy. And there is a change in the order of the energy of these orbitals when we get a lot of electrons in the same sort of vicinity. And that affects how electrons would go into the atom. So for example, we would put electrons here first. Now we could clearly see 2s is the next lowest. We then would fill up our 2p, we would go to our 3s, we would go to our 3p. And here's where the main difference is and throws people off. After you go from 3s to 3p, it is actually the 4s orbital that ends up being lower in energy than the 3d. And that pattern follows. The s is always sort of lower than the d orbitals. It's able to actually penetrate closer to the nucleus, the s orbitals, than the d orbitals. So they actually end up being closer to the nucleus and a little lower in energy. So as the electrons go in, there is a specific order at which you would put them in when you're doing something like electron configuration. So how can you know the order? You can make something like this, which is the actual order that electrons are going in. And if you know what's on the left here, and you know, like we talked about, that if you fill an s orbital, that's a maximum of 2 electrons. If you fill the p subshell, that's a maximum of 6 electrons. If you fill the d subshell, that's a maximum of 10 electrons. And if you fill the f subshell, that is a maximum of 14 electrons. You'll be able to write any electron configuration that you would need to do. How this works is you always start up here, and you basically just follow the arrows to the end. And then when you're done, you come back, and you follow the arrows again to the end. And when you're done there, you come back here, and you keep on following the arrows basically in that pattern. So you may be thinking to yourself, do I have to remember that? The answer is you do need to know the order, the correct order, but you can very easily make this on the paper for yourself, like super easy. And the only thing you have to remember is where these guys start in terms of energy levels. So we talked about the S's start at what energy level? N is equal to 1, right? And then on the second energy level, that is where p orbitals begin, right? And on the third energy level, that is where d orbitals begin. And on the fourth energy level, that is where f orbitals begin. If you can remember that, you can pretty much recreate this. So here's how you could do it pretty easily. All you have to do is go 1s. That is where, that's the only thing there. Then down to the right a little bit, go 2p, right? Then down to the right a little bit, go 3d. And then down to the right, kind of on a diagonal, go 4f. At that point, once you have those guys in, all you have to do is just go numbers 1 through 7 underneath all of them and go to 7. So we could just fill it in and go 2s, 3s, 4s, 5s, 6s, 7s, 2p. We'll just continue on 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, 4f, 5f, and so forth. Hey, even if you go too many numbers, you'll be all right. Even if you just keep filling it in, honestly, you'll never get to those anyways, so you'll be okay, even if you threw in some extra numbers that you probably won't get to anyways. And then now you have pretty much what you need in terms of the orders here, right? And you'll have the proper orders, coming through. And that's so very easy to sort of recreate it for yourself on the paper. All you have to remember is 1, 2, 3, 4, and put the letters and just drop the numbers basically straight down. Any question on how to create that? And like I said, even if you kind of put too many numbers that you'll never get to, it doesn't really matter because you'll never get to them anyways in terms of the order. So if you know both of these things, you pretty much, like I said, can write electron configuration for anything that you need to. So let's write some electron configuration and see what we're talking about. Here again is the orders of those electrons. So electron configuration tells us basically how the electrons are distributed in the atomic orbitals. And those are our S's or P's or D's and our F's. And it tells us basically the energy levels. Remember that if we have a neutral atom, something with no charge, that the number of electrons has to equal the number of protons, which means if you know the atomic number, which is the number of protons for an element, you will also know how many electrons it will have. So let's take a look at our first one here. So we're going to start with hydrogen, which is 1 proton and 1 electron. So if we go to our chart, we're going to start right here. And that will take us to right there. So the electron configuration for hydrogen would be 1s1. And that, by the way, is how you say it, 1s1. The first one here is the energy level. That is the principal quantum number. That is the n value. The S here is the orbital or subshell it is in. In this case, it's the orbital that it is in. And the top number is how many electrons are in that orbital or subshell. So 1s1 is the way you write it. Big 1, lowercase letter, superscript, 1 up on top. Yeah. No dashes, no commas, no weird things people like to put in it when they're writing these things. Another way that we can represent electron configuration is what is known as orbital diagram. An orbital diagram is either boxes or lines to represent orbitals, and we use arrows to represent the electrons. So I'm just going to use lines. In this case, we would have one line for our 1s orbital. And again, you can use a box if you like. And the first electron actually goes in always pointing upwards. So when you do that, that first electron is always pointing upwards. This is what is known as having positive 1/2 spin. By the way, spin is a quantum number as well, which we don't get too much into, but electrons have spin and they're affected by electrical field. The first electron that always goes into an orbital always will be pointing upwards and what is referred to as positive 1/2 spin, basically. Question on that there. Continuing on here to number 2. Now, number 2 is helium. And there's an important rule when we talk about sort of where we're going to put the next electron. So clearly what we just saw with hydrogen is we have in hydrogen 1 electron. That means that this orbital could hold 1 more electron, right, before it is full. Now, how do we place this electron? There's 2 options. We could either put them in going in the same direction, or we could put them in going in opposite directions. These are our 2 options. So there actually is a rule that dictates how the second electron will actually go into the orbital. and that is what is known as Pauli's exclusion rule. And basically what Pauli's exclusion rule says is no two electrons can have the same 4 quantum numbers. We're not going to go deep into quantum numbers at all, really, but the 4 quantum numbers is n, it is L, it is m sub L, and it is m sub S. This basically tells you the energy level. This basically tells you the type of orbital there is, like is it an S, is it a P, is it a D? This basically tells you how many orbitals, and really it tells you their location in 3-dimensional space. And lastly, this is actually the spin quantum number, and this is the spin on electrons. So these are the 4 quantum numbers, and again, we're not going to do too much with it, but I'm just going to kind of show you this so you can understand why we do sort of things here. So what happens, for example, is if we take a 1s orbital and we put this electron in here like we have in hydrogen, and we assign this particular electron right here its 4 quantum numbers, which you will never have to do in this class. But if we actually give it its 4 quantum numbers, it would have a value of n equals 1 because it's on the first energy level. It would have an L value of 0, and 0, by the way, represents an s orbital, basically, quantum number wise. It will have an m sub L value of 0, which is there's only one s orbital, basically, is what that means. And this spin, as we just talked about, because it's pointing upwards, would have positive 1/2. And that would be technically the 4 quantum numbers for that first electron in hydrogen. Now, if we decided to put the second electron in pointing the exact same way, and we did the quantum numbers for this guy pointing the exact same way, it would have an n value of 1. It would have an L value of 0. It would have an m sub L value of 0, and it would also have an m sub S value of plus 1/2. Are those 4 numbers different on each of those electrons? They're exactly the same. They both have the same n number, right? They both have the same L, the m sub L, and the m sub S. That is a violation of Pauli's exclusion rule. They cannot have the same 4 numbers, basically. So the way that they get around not having the same 4 numbers is we do not put electrons in going in the same direction. We actually put the electrons going in opposite directions. So when we look, for example, at the second electron here, it is still on the first energy level, so it still has an n equals 1. It is still in an s orbital, so it's still L equals 0. It is still only one type of s orbital. So the only thing that is different is the actual spin on the electron. It is pointing downward versus upwards. And that gives it a quantum number for spin of minus 1/2. And that difference in the spin quantum number allows those electrons not to have the exact same 4 numbers on all of them. And that does not violate Pauli's exclusion rule. So the take-home message here, and again, you do not have to do any of the quantum numbers or figure out the quantum numbers on anything like that. But the take-home message is here, whenever you put 2 electrons into the same orbital so that this rule is not violated, the first electron always goes in upwards. The second electron always has to go in the opposite direction when they go into the same orbital. Any questions on that? Yeah. It's really outside the purpose of this class, but that's really, it's actually the quantum numbers come actually before the orbitals. It is what actually determines what type of orbital it is, and 0 is designated for the L value as an s orbital. If you had an L value of 1, for example, that's designated for p orbitals, and if you have like an L value of 2, that's like d orbitals, and so on. Exactly, yeah. And actually, that's why, for example, we have, when we say, hey, there's like 3 different p orbitals, there's like, 5 different d orbitals. It's because actually the quantum numbers, they actually are the reason why there's many orbitals. They're really the basis behind it. So we're not going to get into this at all. In 1A, you'll get into it and why it is and stuff like that. But it's actually the basis for really why there's all these different types of orbitals. All right, so again, let's take a look at helium now that we talked about it. Once again, we're going to start with up here, and we have 2 electrons. So we're going to go again here to this first guy, and the electron configuration for helium, which has 2 electrons, 1s2. Again, that is the energy level. The electrons are hanging out in the s orbital, and now there are 2 electrons in that s orbital. And if we were to draw our orbital diagram for this, we would have a 1s box or line. First electron goes upwards, and based on what we just talked about, second electron goes downward in this case. This arrangement where electrons are going in opposite sort of spin, this is what is referred to as having paired spin. They basically cancel each other out, kind of plus a half, minus a half. They sort of cancel their spin out basically in that orbital. Can that orbital take any more electrons at this point? No. So if we have more electrons, we need to continue down our path here, and we will now have to kind of swing back and come back around to here. So let's do that here. Let's go to lithium, which is 3. So lithium, which is 3, would be, again, if we start here, always 1s2. We're going to then swing back around to 2s. So that would give us 1s2, 2s1. Once again, that is how you write it. There is no like dashes, commas, or anything like that. That is a total, if you count up the top numbers, 3 electrons. So that is a total of all 3 electrons that are present. There are how many electrons on the first energy level in this case? 2, right? How many electrons on the second energy level? 1. That's what the 2 means here. So those are the energy levels. So that means n is equal to 1. That means this guy is on the second energy level. So we have 1 electron now on the second energy level. We have 2 electrons on the first energy level. That means when we draw our diagram here, we'll need 2 lines. Now, if you really want to do this energy correct, the 1s should be here and the 2s really should be higher in energy. I'm just going to go side by side to save space, but really you should build it up kind of energy-wise, but it's okay. I'm going to go side by side. First one's going to go in up. Second one's going to go down. My next one should go which way? Up, right? And that would be our 3 electrons. We can now see for our 2s orbital, we can put how many more electrons in there before it's filled? 1 more electron. So let's do that one, which would be our next guy on the periodic table there. And that's going to be beryllium, which has 4 electrons. It's going to be 1s2, 2s2. Again, if we draw our orbital diagram, we'll have a 1s box, a 2s box. We're going to go up, we're going to go down, we're going to go up, and we are going to go down. And now we are filled at this point. We now have how many electrons on the second energy level? On the second energy level, which is this, we only have 2. On the first energy level, we still have 2, right? We have a grand total of 4 that has been basically put in there. Any questions on that there? Now, continuing on here, we've obviously come through here. We've zigged back here. We now are going to enter into the 2p next, right? And that 2p subshell is made up of 3 orbitals, which can hold a maximum of 6 electrons if you fill them all up. So let's go to number 5. That would be 1s2, 2s2, and now 2p1 in this case. We draw our orbital diagram for boron. We need a box for 1s. We need a box for 2s. How many lines do we need for the 2p? We need 3 of them, right? There are 3 different orbitals. This is like px, py, and the pz orbital, right? Those 3 different p orbitals that make up the subshell. Put it in our electrons. We go one up, one down. We go one up, one down. And here we go left to right, going with upwards here at this point. How many electrons are now on the second energy level? I see 3 fingers, so I'm going to go with that as a 3, what you said, I suppose. So 2 there and 1 more there, right? So they're both on the second energy level, so that is 3. Still hanging out with only our 2 on the first, which is the maximum could really put on that energy level, as 1 squared is 1, 1 times 2 is 2, right? So that's the maximum if you label up. Question? Is it okay to have these guys empty? Like here? Yeah, you should have them. If you're drawing the orbital diagram, you should have the 3 boxes and just leave them empty. Yeah. Now we come to a situation where we're going to put another electron in there, and obviously our p subshell could hold another 5 electrons before it's full. The question is, where do we put our next electron in this guy? So do we put it next to it there and pair it up? The other option would be to put it next door to it. And there is actually a rule that helps us decide sort of which way electrons should go into a subshell where there's multiple orbitals. And that rule is Hund's rule. And basically, Hund's rule says that the most stable arrangement for electrons in a subshell where there's multiple orbitals is one that maximizes parallel spin. So what does that mean? It means that when we look at this, if I put the electrons in the same orbital first, that is paired spin, yeah, as we talked about. But if I throw my electrons in one at a time, they're all heading in the same direction. They're all parallel to each other. And that is the way that we do it. So when you have a subshell that has multiple orbitals, they go in one at a time in the upwards position until you have nowhere else to go. And at that point, then you come back and start pairing off. So they go in one at a time upwards and then come back and pairing off. So following Hund's rule tells us how we should distribute these electrons in a subshell with multiple orbitals. So when we get to carbon, which is 6, we're going to go with 1s2, 2s2, 2p2, 2, 4, 6 electrons. We will have our 1s, our 2s, and our 2p. We will go up, down, up, down, up. And now to maximize parallel spin, we will actually put the electron going upwards in the orbital to the right. And we will continue that in the same direction until we run out of orbitals and then has to go back and pair up at that point. Any questions on that there? All right, we're lit up there for today, I think.